Prime numbers are often described as the building blocks of mathematics, and for this reason, mathematicians have expended immense energy to study them. Indeed, every positive integer greater than 1 either is prime, or, like 6, can be factored into primes. 2 and 3 are prime numbers that multiply to 6, and these two numbers cannot be factored any further. There is, despite all our efforts, still a great deal of mystery regarding the primes, and men and their computers all over the world are searching for bigger and bigger primes by the day. But one of the most significant results that has been proven about prime numbers is the prime number theorem. This theorem was proven in 1896 by Jacques Hadamard and Charles Poisson, and it gives us a rough idea of how prime numbers are distributed. This on the left is the prime counting function, and what this theorem says, roughly, is that the number of primes less than or equal to x is about x divided by log x. So this expression on the right is just an approximation of the prime counting function, but as x gets very, very large, the relative error of this approximation approaches 0. Proving the prime number theorem is a pretty difficult task, but it does have two somewhat more basic consequences. Firstly, it implies that the number of primes is infinite, which is a basic fact dating back to Euclid, and there are many interesting proofs of that result. Perhaps more interesting is this second consequence. While there are infinitely many primes, this second consequence basically states that the prime numbers get increasingly rare as we go further down the number line. For example, suppose this function, instead of counting the prime numbers less than or equal to x, was counting the positive even numbers less than or equal to x. Then, if we plugged in x equals 100, certainly there are 50 positive even numbers less than or equal to 100, so this would be 50 divided by 100, which is 1/2. So no surprise, this would be telling us that the even positive integers make up half of the positive integers. Every other positive integer is even. But since this counts prime numbers, the ratio it approaches is not 1/2, it is in fact just 0. If we let x equals 100 with this prime counting function, well, how many prime numbers are there less than or equal to 100? Not that many. It's certainly fewer than half, and as x gets larger and larger, that proportion gets increasingly small. In the long run, it gets arbitrarily close to 0. And this is what we mean when we say that prime numbers are quite rare, and of course, it is not a trivial task to find them. And while the prime number theorem is quite difficult to prove, this significant consequence of the theorem can be proven with a little bit of gumption and some elementary mathematics. Today, I'd like to show you that very clever proof of this beautiful result concerning prime numbers and how they get arbitrarily sparse. Outside of basic algebra, to understand this proof, there are 4 key things you'll need to understand. 1, you'll need to know the prime counting function. 2, you'll need to know this little quirk. If we have a number whose digits are maximal in the base, in this case it's base 10, so the biggest digit is 9. If we have a number like that and add 1, then what we get is the next power of the base, in this case 1000, which is 10 to the power of 3. We're going to apply this property in base 2. Third, you need to understand sets, subsets, and the binomial coefficient. And fourth, you need to understand what a logarithm is and some basic log properties. I'm going to explain all 4 of these things before we move into the proof, and this video has chapters, so if you want to skip any or all of the explanations and jump to the proof, you can do that. With that said, let's begin with the prime counting function, which I've already briefly described. The prime counting function, pi of x, counts the number of primes less than or equal to x. So for some examples, pi of 1, the prime counting function evaluated at 1, is 0. There are no prime numbers less than or equal to 1. On the other hand, pi of 2 is equal to 1. There is one prime number less than or equal to 2, namely the number 2 itself. What about the prime counting function evaluated at 6? What is this equal to? Well, we have 2, 3, and 5 as prime numbers less than or equal to 6. So this is equal to 3. And if you run the numbers, the prime counting function evaluated at 100 is actually equal to 25. That's because there are 25 prime numbers less than or equal to 100. Now, you may be wondering what the prime counting function has to do with pi. Anyways, let's move on to topic 2, the funny little thing with the bases. This 999 is written in our normal decimal system. That's base 10. But let's say I wrote 777 in base 8. So I'll put a little 8 here as a subscript to indicate that this is in base 8. What is this equal to in base 10? This is just a quick explanation of how number base systems work. Since the first digit here is 7, that's representing 7 times 8, because 8 is the base, to the power of 0. The next digit, which happens to also be 7, is representing 7 times 8 to the power of 1, and so on. The powers of 8 increase as we go up the digits, so the next digit represents 7 times 8 to the power of 2. This is, of course, just like how this first 9 represents 9 times 10 to the 0, that is 9 units. This next 9 represents 9 times 10 to the 1, or 90, and then 9 times 10 to the 2, or 900. And this is why in base 8, the biggest digit we need is 7, because for example, if we had 8 copies of 8 to the 1, well, that would actually be a copy of 8 to the 2, and so that would be written over here. Regardless, if we have this number, which is composed of maximal digits in a base, in this case 777 base 8, if we add 1 to that, still working in base 8, this is equal to the next power of the base, the next power of 8. So that would be written as 1, 0, 0, 0, which in this case is representing 1 copy of 8 to the power of 3. So everything I've written here is in base 8, except this final result. Like I said in the proof, we're going to use this property with binary, which is base 2. Suppose I had 1111 in base 2. Keep in mind, in base 2, 1 is the maximal digit, or we would call it a bit in base 2. This is saying that we have 1 copy of 2 to the 0, we have 1 copy of 2 to the 1, we have 1 copy of 2 to the 2, and we have 1 copy of 2 to the 3. And so if we add 1 to this, just like adding 1 to a number that's made up of a bunch of 9s in base 10, everything rolls over and we get the next power of 2. So we would get 1, 0, 0, 0, 0, which is representing 1 copy of the next power of 2, so that's 1 copy of 2 to the power of 4. And really, the key takeaway here is that if we add up a bunch of consecutive powers of 2, starting with 2 to the power of 0, this sum, which is represented by this binary number, is going to be less than the next power of 2. 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3, that's less than 2 to the 4. And if we added 2 to the 4 to this, that would be less than 2 to the 5, and so on. Next up, sets, subsets, and the binomial coefficient. A set is an unordered collection of distinct objects. For example, this set contains 3 objects. We call them elements. It contains A, B, and C. If we call this set S, a subset of S is some other set whose elements all belong to S. So for example, if I took another set that contains A and B, that would be a subset of S, which we could write like this. Again, it's a subset of S because all of its elements are also elements of S. If we put something else in this set, such as the sin of gluttony, it would no longer be a subset of S because S doesn't contain that sin. Now, this particular subset of S has 2 elements, so we may ask how many 2-element subsets are there of S? To count that, we can easily use what's called a binomial coefficient. Certainly, the number of 2-element subsets of S is just the number of ways we can pick 2 of the elements from S to be in a subset. And this, called the binomial coefficient, is the notation we use for that. This is read 3 choose 2. It is, in this context, the number of ways we could pick 2 elements from the 3 elements in S to make our 2-element subset. It's easy to see that 3 choose 2 happens to equal 3. We could choose A and B, A and C, or B and C. A different question is how many subsets total are there of the set S? Certainly there are more than 3, because 3 is just the number of 2-element subsets. So if we want to count all subsets total, that will definitely include more possibilities. It's important to note that technically the set which contains nothing is considered a subset of S, and the set S itself is considered a subset of S. With that in mind, counting all subsets is a fairly easy task, because S has 3 elements, and for each of them, we have 2 choices when constructing a subset. Either include the element in the subset, or do not include the element in the subset. So if we're trying to count subsets of S, every one of these 3 elements gives us 2 choices when constructing subsets. Hence, there would be 2 to the power of 3 subsets. In the case of S, it's 2 to the power of 3, but in general, for a set that contains n elements, its number of subsets would be 2 to the power of n. And again, that's because every one of those n elements gives us 2 choices when constructing subsets. One last thing for the binomial coefficient is that I should mention how it's actually calculated. I'll leave a link in the description to a video where we derive this formula and explain where it comes from, but n choose m is equal to n factorial divided by m factorial multiplied by n minus m factorial, where the factorial of a number is the product of that number with all positive integers less than it. Finally, understanding the log function. I'm not going to go into great detail here, but I want to make sure you know the properties we're going to use. In short, the logarithm function is the inverse of exponentiation. So for example, if we had log base 4 of 4 to the power of x, the log function is going to undo this exponentiation, where x is in the power there, and so the result of this function is just going to be x. Now, every logarithm has a base. That's part of the function. In this case, everything canceled out and left us with x, because we have to raise the base of 4 to a power of x to get this input of 4 to the power of x. If, for example, we took the base 2 log of the number 8, we would get 3, because we have to raise the base of 2 to the power of 3 to get 8. Now on this little card, I wrote the log function without a base, and typically if it's written without a base, we assume that it's the natural log, and so its base is e. If you don't know what that is, it's just some ugly number. It's equal to about 2.718. Indeed, the previous times in the video where you've seen this function without a base, this is the base that is assumed, and that's called the natural log. So the logarithm function undoes exponentiation, and it has one other key property we're going to use several times throughout this video, which is that if we take the logarithm of a to the power of n, we can actually take the power of n out of the logarithm as a factor. Thus, we could rewrite this as n times log a. Alright, with all of that, we are ready for this incredible proof of the fact that the density of the prime numbers is 0. As we progress further up the number line, the prime numbers get increasingly scarce. Let's do it. We begin the proof with a question. How many n-element subsets does a set with 2n elements have? So our set has 2n elements, and we're asking how many n-element subsets does it have? The answer, of course, is 2n choose n. It can be found using a binomial coefficient. So this is the number of n-element subsets in a set with 2n elements. Now, how many subsets are there total of a set that has 2n elements? Well, from our previous discussion, we know that would be 2 to the power of 2n, because for every one of those 2n elements, we would have 2 choices when constructing a subset, either include it or exclude it. Since this counts n-element subsets, and this counts all of the subsets, certainly this is less than this. Now we're going to use an exponent property here. If we have 2 to the power of 2 times n, we can raise 2 to the power of 2, evaluate that, and leave n in the exponent. So 2 to the power of 2 is 4, so this is equal to 4, and we would still have n in the exponent. Okay, key takeaway from this is that 2n choose n is less than 4 to the power of n. With that established, we're going to do some more work with 2n choose n. We know what this is equal to because we know the formula for binomial coefficients. This is equal to 2n factorial divided by n factorial times 2n minus n factorial. Now remember, 2n factorial is the product of 2n with all positive integers less than it. Similarly, n factorial is the product of n with all positive integers less than it. So there's going to be a lot of cancellation there once this factorial in the numerator gets down to n and the positive integers below it. All of those would cancel out with n factorial, and all we'd be left with in the numerator is the product of the positive integers between n plus 1 and 2n, those that weren't canceled out by the n factorial. As a result, in the numerator, we're left with that product. All of those positive integers greater than n, so n plus 1 times n plus 2, and so on, all the way up to 2n. In the denominator, that n factorial on the left got canceled out by the 2n factorial, and here, 2n minus n, that is just a single n. So this is just n factorial, which of course is 1 times 2 times 3, and so on, all the way up to n. Alright, now what do we actually know about this number, 2n choose n? Well, for starters, it's definitely a positive integer, because remember, it counts the number of n element subsets of a 2n element set. The number of subsets is definitely a positive integer, and so this is a positive integer. Also, all of these positive integers between n plus 1 and 2n, there are going to be some prime numbers there, and none of them are going to be canceled out by what's in the denominator, because of course they are prime. Any prime number in this product from n plus 1 to 2n, if we were to call it p, it certainly can't be canceled out by some number that's between 1 and n, because all of those numbers are smaller and are obviously not factors of p because p is prime. The exception, of course, being 1, which isn't going to cancel it out. Hence, what we know about 2n choose n is that it's a positive integer who has as its prime factors all of the prime numbers from n plus 1 to 2n. Whatever prime numbers are in there, those are factors of this positive integer. And of course, any such prime number in that product is greater than n, because this product starts greater than n at n plus 1 and only gets bigger from there. So we already said 2n choose n is less than this, but now we're going to bust out the prime counting function to put a lower bound on 2n choose n. After this discussion, we know that 2n choose n must be greater than n to the power of pi of 2n minus pi of n. That's because remember, the prime counting function counts the number of primes less than or equal to the input. So this is all of the primes less than or equal to 2n. This is all of the primes less than or equal to n. Hence, when we subtract them, we get exactly the number of primes between n plus 1 and 2n. All of those primes, which must be greater than n, are factors of 2n choose n, and so 2n choose n must be greater than n itself raised to the power of that number of primes. If we were to just write out the product of the prime factors of 2n choose n that we know from this product in the numerator, it would be a product with more than this many terms, where every single number in the product is greater than n. So that's how we know this is greater than this. Now, our connective tissue is the 2n choose n. We know that 2n choose n is greater than this, but it's less than this. Hence, n to this power must in fact be less than this also. So we arrive at this inequality, that n to the pi of 2n minus pi of n is less than 4 to the power of n. And now we're going to take the logarithm of both sides of this inequality and exploit some of its properties to get a more useful expression. It's important to note that the logarithm function is an increasing function. It looks something like this. It's increasing, so we can take the logarithm of both sides of an inequality while preserving preserving that inequality. Thus, we have log of this on the left is less than log of 4 to the n on the right. Again, I haven't written the bases here, so we're assuming the base is e, and those nice properties of the logarithm I described would work for any base. It is high time we exploit those nice properties. So, like I said, the exponent of this thing in the logarithm, the pi of 2n minus pi of n, we can take out as a factor. Similarly, the exponent on this side, that n, we can take out as a factor. Taking those exponents out as factors, we arrive at this nice inequality where we have pi of 2n minus pi of n getting multiplied by log n, which is less than n log 4. Again, n was the exponent, which we've now taken out as a factor. And now we're going to divide both sides of this inequality by log n. So it is important to note that the logarithm of a positive integer greater than 1, which we're assuming n is, that's always going to be a positive number. So we don't have to worry about dividing by 0 or dividing by a negative here. So dividing both sides by log n, on the left, we're just going to be left with pi of 2n minus pi of n. And on the right, we're going to have n times log 4 now divided by log n. Now 2n, of course, is a multiple of 2, but at this point, we're going to stop talking about multiples of 2 and start talking about powers of 2. So let's suppose that n is itself, in fact, a power of 2, and thus 2n is, of course, a power of 2. So we're going to say that 2n is equal to 2 to the power of k. This implies, of course, that n is equal to the previous power of 2, namely 2 to the power of k minus 1. This is in fact going to simplify things a bit. We'll be able to get up to a heck of a lark, and in the end, it's all going to work out. So let us then rewrite this inequality with the new assignment that 2n is equal to 2 to the k, and n is equal to 2 to the k minus 1. So this is what we have on the left, and then on the right, n will be replaced by 2 to the k minus 1, both there and there. So we have 2 to the power of k minus 1 times log 4 still. The 4 is not going to change. And this is divided by log n, but n is 2 to the k minus 1. Now let me just circle this. We're going to work off to the side and do a couple devious tricks to rewrite this expression. Firstly, in the numerator, we're still going to have 2 to the power of k minus 1. But then log of 4, we're going to write 4 as a power of 2. Hence, it's log of 2 to the power of 2. In the denominator, we have that power of k minus 1 being applied to 2, but this is in a logarithm, and so we can take that power of k minus 1 out as a factor. Hence, we rewrite the denominator as k minus 1 multiplied by log 2. But then, in the numerator, notice this 2 in the log has a power of 2. Again, we can take powers out as factors, so we're going to take that power of 2 out as a factor of 2, which means instead of having k minus 1 factors of 2 in the numerator, we will in fact have k minus 1 plus 1, or k total factors of 2 in the numerator. And once we take that power of 2 out, this is just going to be log 2 in the numerator, which would cancel out with log 2 in the denominator. And so in the end, we would arrive at this expression, 2 to the power of k in the numerator divided by k minus 1 in the denominator. Again, that's because we took this power of 2 out of the log, so log 2 cancels out, and that additional factor of 2 just means we have k factors of 2 here instead of k minus 1 factors. So now we have that this difference of prime counting functions is less than this fairly simple expression. I hope you're having fun at this point. Now we're going to do something really wacky. We're going to sum both sides of this inequality from k equals 2 to k equals 2m, where m is just some positive integer greater than 2. So again, on both sides of the inequality, we will be summing from k equals 2 to k equals 2m. Now when we do this on the left, what's going to happen is what's often described as telescoping, because we're going to have, some power of 2, but then minus that power of 2, and some power of 2, and minus that power of 2. Almost everything in the sum is going to cancel out, and we're just going to be left with 2 terms. On the right, of course, we're going to have the sums of a bunch of powers of 2, which we're going to be able to simplify because of what we know happens when we add powers of 2. Let's first dabble with this left side a bit, just so you can see that telescoping pattern in action, which I described. Again, this is the expression, and we're going to sum from k equals 2 to k equals 2 to the m. So let's write a few of those terms and see what it looks like. We would start with k equals 2. So we would have pi of 2 to the power of 2 minus pi of 2 to the power of 2 minus 1, which is just 1. Then we would add this to the k equals 3 case. When k equals 3, we would have pi of 2 to the power of 3, and then minus pi of 2 to the power of 3 minus 1, so pi of 2 to the power of 2. And now you can see how that first pi of 2 to the power of 2 is going to cancel out with this pi of 2 to the power of 2. And this pattern of cancellation will continue as these powers continue to increase for further terms in the sum. When k equals 4, we would have pi of 2 to the power of 4 minus pi of 2 to the power of 3, which would cancel out with this guy. The only things that won't get canceled out are this minus pi of 2 from the very first term, and the very last term with that biggest power of 2, which would be when k is equal to 2 times m. So in the end, after almost everything cancels out, we would just be left with pi of 2 to the power of 2m minus that very first term, pi of 2. So that's what's going on the left side of this inequality once we sum from k equals 2 to 2m. Now let's spend some time with the right side doing the same thing, but different simplification. So on the right side, we have 2 to the power of k divided by k minus 1, and we're summing from k equals 2 to 2m. Then it's straightforward enough to write out the relevant sum. When k equals 2, we have 2 to the power of 2 divided by 2 minus 1, so divided by 1. Then when k equals 3, we have 2 to the power of 3 divided by 3 minus 1, so divided by 2. Then when k equals 4, we have 2 to the power of 4 divided by 3, and so on. This goes on. Remember, we're going all the way up to k equals 2m, so eventually k would have to pass m. That would happen like this. We would have 2 to the m divided by m minus 1, and then we would have 2 to the m plus 1, and it would continue. I'm running out of space. It would go all the way up to k equals 2m, where we finally would arrive at 2 to the power of 2m divided by 2m minus 1. Now in the end, we're going to use this as an upper bound. So what we're going to do is simplify it in a way that makes it bigger. For starters, everything from here to here with that denominator of m minus 1, we could just get rid of all of those denominators. Certainly, that would only make the expression bigger. Similarly, everything from here onwards, everything with the denominator of m or bigger, if we just gave all of those terms a denominator of m, that would again only make the expression bigger, because in all of these cases, we would be dividing by a smaller number, just m, instead of something like m plus 1 or m plus 5 or 2m minus 1. So this whole thing is going to be less than, again, what we're doing is getting rid of all denominators up to m minus 1, and then for all those denominators from m onwards, we're going to change them all to just be m, and so we can write them in a single fraction. The result is this, and this is where we finally use that discussion about binary numbers to make this just a little bit bigger and a lot a bit simpler. This here is the sum of every power of 2 from the second power up through the mth power. Now we know even if we had every power of 2 from the 0th power up through the mth power, that would still be less than the next power of 2, which is the m plus 1th power. And here, we don't even have all of those powers of 2. We're missing the power of 0 and the power of 1. So when we add all of these up, certainly that's less than 2 to that next power, m plus 1. Because remember, adding consecutive powers of 2 in binary, that looks like a binary number with maximal bits, which is always less than the next power of 2. Now, same exact idea with the numerator in this fraction. This is the sum of a bunch of powers of 2 from the m plus 1th power up to the 2mth power. Even if this had all powers of 2 from the 0th all the way up through the 2mth, that would be less than the next power of 2, the 2m plus 1th power. But this is missing a bunch of powers from 0 to 2m. So for sure, this numerator is less than the next power of 2, which is 2 to the power of 2m plus 1. And so we replace it with that bigger number, which is 2 to the power of 2m plus 1, and still with the m in the denominator. Alright, so that is the simplified form of the right side of this inequality after doing that summing from k equals 2 to 2m. So So starting to bring things together now, on the left side, remember, we have pi of 2 to the 2m minus pi of 2. We know what pi of 2 is equal to, so instead of writing minus pi of 2, I'm going to write minus 1. There is one prime number less than or equal to 2. And what is this less than? Well, as we just saw, it is less than this. All right, we are really getting somewhere now. Here's what we're going to do. We're going to add 1 to both sides of this inequality, so this pi is going to be by itself on the left. And then remember, 2 to the power of 2 times m, we can do 2 to the power of 2 first and leave m in the exponent, so that this will be pi of 4 to the power of m. So on the left, we're going to have pi of 4 to the power of m, and this is less than, we've added 1 to both sides, so we have 1 plus the rest of this. Right now, our only variable is this positive integer m, but remember, in the end, we're trying to make a conclusion about some function of positive real numbers, as that real number x goes to infinity. So now we're going to have to make some assertion about positive real numbers in order to get x involved. And here is that key assertion, which is going to let us start popping in some x's into that inequality. For every real number x that is greater than 0, there certainly exists some positive integer m, so that x is between the mth power of 4 and the m minus 1th power of 4. That is, 4 to the power of m minus 1 is less than x, which is less than 4 to the power of m. Hopefully it's easy for you to accept this fact on its face. For any positive real number, I could find 2 consecutive powers of 4 where they jump across x. For example, if x equals 20, well, 4 squared is 16, which is less than 20, and 4 cubed is 64, which is greater than 20. Although I should put a less than or equals here because it is possible that x is itself a power of 4. But this inequality, that x is less than or equal to 4 to the power of m, will allow us to replace this part of the inequality, the smaller part, 4 to the m, with x, which we know is a smaller number. Now, in order to get x involved on the right side of this big inequality, we're going to need to take logarithms of this inequality. We're going to take log base 4 of this entire thing. When we take log base 4 of 4 to the power of m minus 1, that's going to cancel out with the base of 4, undoing the exponentiation and leaving us with just m minus 1. In the middle, of course, log base 4 of x is just log base 4 of x. And on the right, log base 4 of 4 to the m undoes the exponentiation and leaves us with just m. We can then add 1 throughout this whole inequality to get that m is less than log base 4 of x plus 1 is less than or equal to m plus 1. Now, because we know log base 4 of x plus 1 is greater than m, we can replace this m and this m on the right side of this inequality with that bigger number, log base 4 of x plus 1. On the other hand, this denominator we would want to make smaller so that we're just making the right side of the inequality bigger. And well, we know that m is at least as big as log base 4 of x, so we could replace m in the denominator with this smaller number, log base 4 of x. Alright, so beginning to get x involved here, which is just some arbitrary positive real number, pi of x. We know that we can find some m so that pi of x is less than or equal to pi of 4 to the power of m, because 4 to the power of m is at least as big as x. But we know that pi of 4 to the power of m is less than this, where we can now start to make those substitutions I mentioned a moment ago. We're going to replace m with log base 4 of x plus 1. There's log base 4 of x plus 1, and don't forget there was already another plus 1 in that exponent. We're going to do the same thing with this m, but then this one in the denominator we'll replace with the smaller number, log base 4 of x. That gets us here, and we are now very close. We have the prime counting function, pi of x, bounded above by this giant mess. So we're going to take this big giant mess, do some simplification, and then in short order, we'll be done the proof. So I'm starting to rewrite the right side of the inequality here. Note that in the exponent of this first 2, we have log base 4 of x plus 1 plus 1. So that's 2 plus log base 4 of x. Then over here, distributing the 2 through those parentheses, we would have 2 times log base 4 of x plus 2, and then there's that plus 1, so in the end it would be plus 3. Now, this is equal to 1 on the left, that's unchanged, and then 2 to the power of 2 plus log base 4 of x, we can rewrite this as 2 to the power of 2 times 2 to the power of log base 4 of x, using our exponent rules. Of course, 2 to the power of 2 is just 4, so we would have 4 multiplied by 2 to the power of log base 4x. But instead of writing it as 2, I'm going to write it as 4 with a square root. Now, the square root of 4 is the same as 4 to the power of 1/2, so in the end, it's 4 to the power of 1/2 multiplied by log base 4 of x. Again, a power of 1/2 is the same as the square root. Square root of 4 is 2, so this is really just a funny way of writing 2 to the power of log base 4x. Now we're going to get up to some similar tricks with this fraction. 2 to the power of 3 plus 2 log base 4x. We can write that as 2 to the power of 3 times 2 to the power of that log. Now, 2 to the power of 3 is 8, so let's just write the 8 to the left of the fraction. And then here's what's going on with the fraction. We have 2 to the power of 2 log base 4 of x. We could just raise 2 to the power of 2 first, giving us 4, and leave log base 4 of x in the exponent. In the denominator, we still have log base 4x. Now, all of this quirky rewriting has gone a long way to enable us to take advantage of our log properties. Because this logarithm has a base of 4, and it's in the exponent of a 4, the log and the 4 will cancel out, and we'll just be left with x, which will have that 1/2 in its exponent. Hence, we'll have 4 times x to the 1/2. But x to the 1/2 is just a square root of x, because a power of 1/2 is a square root. A similar thing happens with the fraction. 4 to the power of log base 4x, the logarithm undoes the exponentiation, and so we're actually just going to be left with the x. This is then 8x divided by log base 4x. And now it's all coming to a head. On the left side of that inequality we were working with, we have pi of x, the prime counting function evaluated at a positive real number x. And we know that it's less than this. And we've just shown that this is equal to this. And so at last we have that pi of x is less than this expression. But remember, our theorem that we're trying to prove isn't about pi of x, it's about pi of x divided by x, which clues us into the fact we should divide both sides of this inequality by x. Then on the left, we'll have that expression we're actually interested in. Of course, x is a positive real number, and so dividing by it doesn't cause any issues. So on the left, we have pi of x divided by x. On the right, we have 1 divided by x, and then 4 times the square root of x divided by x. If you just used your exponent rules, it's easy to see that is 4 divided by the square root of x. And then, of course, this last term, that x in the numerator, is just going to cancel out, leaving us with 8 divided by log base 4x. And then remember, the question is what happens as x goes to infinity? This means what is happening as x gets arbitrarily large. We know that this guy on the left is positive, because the prime counting function is positive, and x is positive. So it's going to be bounded above by this guy, and bounded below by 0. We could even write that it is certainly at least 0. But then what happens to this upper bound as x gets arbitrarily large, as x approaches positive infinity? Well, this is 1 divided by an arbitrarily large number, so that's certainly going to 0. This is 4 divided by an arbitrarily large number, that certainly is 0 as well. It's a whole nother matter entirely to show that log base 4 of x gets arbitrarily large, but if you understand the logarithm function, it's easy to see that indeed this too gets arbitrarily large. So this is a fixed number, 8, divided by something getting arbitrarily large, hence it's certainly approaching 0. Since pi of x divided by x is at least 0, but we also know that it's less than something, which is approaching 0, that then finally establishes that pi of x divided by x, as x gets arbitrarily large, approaches 0. So this limit is equal to 0. So what portion of the positive integers do the prime numbers make up? Well, 0. They have density 0. There are very few primes viewed this way. So what's all the hullabaloo about prime numbers? Well, this short little proof demonstrates it. They are scarce. They are indeed glistening diamonds hiding in the shadowy corners of an infinite cave of darkness.
From my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tune of words and just how I say shit. And let me speak my poetry to your face. It's not in the mid if you ain't listening. Not infinite if you ain't really into it.